Welcome to Econ 317. In this instruction video, we will go over the application of derivatives in the optimization problems. So let's start with, first we want to deal with optimization problems in economics. So we'll come up with the description, but we also want to learn how do we apply the notions of derivatives in solving the optimization problem. So remember, we have an objective function of one variable, so f of x, which we want to solve, for which we want to either maximize, we wish to maximize, or maybe minimize. So this is the optimization problem. Okay, so and we believe the function is well behaved in the sense of, if I draw the graph of the function, it looks something like this. So I have x on the horizontal axis, independent variable f of x, the function value, and let's say the graph looks something like this. So what I can see from this graph is that, let's say this x value is 1. Maybe I assign value 3 here, maybe value 5 here, and then we can now come up with our arguments. So we see the function attains a maximum value at x equal to 1. So f of x attains a maximum at x equal to 1. And when I say it attains a maximum at x equal to 1, I could make it more precise, because I also see that the function attains again a maximum value, maybe different from 1 at x equal to 1, but at x equal to 5. So I will make it more precise to claim that the function attains a local maximum at x equal to 1. F of x attains a local maximum at x equal to 1. Okay. For x equal to 3, now we can make a more precise statement. It attains a minimum value. So f is at a minimum at x equal to 3. And we see there is only one minimum. So we can now say not only it is a minimum, f attains a global minimum at x equal to 3. And here in this graph we can see, as we are looking at the function moving from x values close to 1, but from the left hand side we can see slope of the tangent to the graph is positive, like here. I will show this slope appears to be positive, continue to remain positive as I get closer and closer to x equal to 1. And so on the left hand side it is positive, on the right hand side it is negative, but at exactly x equal to 1, the slope of the tangent appears to be flat, to be 0. So the tangent appears to be flat at x equal to 1. And that is the situation we obtain when we claim that the function has attained a local maximum at x equal to 1. I can make similar claim when the function attains the minimum value, that is at x equal to 3, that the slope of the tangent to the graph at x equal to 3 is again 0. Same observations hold true even at the second local maximum x equal to 5. So this helps us apply the notion of derivatives in finding out points at which the function either attains a maximum or a minimum. So I will write it up. So first let me use a numerical value. So I will say at x equal to 1, we know the function f of x attains a local maximum. So I want to relate this observation to the derivative of the function at x equal to 1. So I will rewrite it at x equal to 1, since the function f of x attains a local maximum. Let me write a local maximum. The derivative of the function at point x equal to 1 is 0. Okay, but x equal to 1 was one instance. Maybe we draw another graph, the value of x will change. And but again, if we say that at the new value of x, the function attains a local maximum, then it must be true that the derivative of the function at that point is 0. So let me write this now in more general case. If f of x, the function, attains a local maximum at point. So let me now identify the point. I will say x star, then the derivative of f at x star is 0. I wrote in words, I can write the mathematical expression at x star, the derivative of the function is 0. This was the situation when we know that the function has obtained a local maximum. But we also saw from the graph the same condition holds even when we have the function attaining a local minimum. So I will write that also for the sake of completeness. So if f of x attains a local minimum at, now I will choose deliberately a different point, so I will use notation x bar, then the derivative of f of x at x bar is again 0. So let's write it more precisely. at x bar, the derivative is 0. Okay, so two things. First, we are able to observe that once we know that the function has obtained or has attained either a local maximum or a local minimum, the derivative is a useful idea to utilize. We can find the derivative of the function at that point and it will turn out to be 0. Okay, and then this holds true for each one of the point of local maximum, not exactly one. So even though it is quite useful, still there are some gaps remaining. So what if, so I will first make a formal statement, the necessary condition of the derivative of the function attaining local maximum or local minimum at x star is the derivative being equal to 0 is the derivative of the function at that point equal to 0. Okay, so I will call it the necessary condition. Is it sufficient? And I will give an example to claim that no, it is not sufficient. However, this condition is not a sufficient condition. So, to give you a counter example, here is an example. I want to show that a function has derivative equal to 0 at a particular point, and function does not attain either a local maximum or a local minimum at that point. That would be a counter example to the necessary condition being sufficient. So consider the f of x. I'll write it as y equal to f of x equal to x to the power 3. Let me just draw a graph for this function. So we have x here, we have y here, and this is the cubic function. So it goes like, it is 0 at x equal to 0, and then it is increasing all through. No, let me draw another one. It doesn't look good, so I will draw another one. Just to emphasize that the function passes through the origin. I will be careful, and it is a smooth graph. So I have x here, I have y here, and so at x equal to 0, y, which is x cube, equal to 0. That's one. But note, this function is strictly increasing. Y equal to x cube is strictly increasing. It never goes down. Okay. And I want to see whether it has derivative equal to 0 at some point. So let's find out the derivative. y equal to x cube, so dy over dx is equal to 3x square, which is 0 at x equal to 0. But you can see from this graph at x equal to 0, the derivative is 0, but the function is neither a maximum nor a minimum at x equal to 0. So I'll write it. However, the function y equal to x cube neither attains a maximum nor a minimum at x equal to 0. So we call such points as inflection point. This point is called an inflection point. Okay, so this example tells us that the necessary condition of the derivative attaining value 0 is not sufficient. We need some more additional conditions to figure out whether the function indeed has a point of maximum or a minimum, or it is a point of inflection. So with this, now I will write down the application of the necessary condition to a formal optimization problem. So let's say our optimization problem is a maximization problem. I want to say y is equal to f of x, and I want to maximize this. Maximize y, which is a function of f of x, by choosing the value of x to be any number, any real number. If this is the problem assigned to us, I will say that the objective function is given as y, which is a function of x. The choice variable, this is the variable whose value we will change to find out the point of maximum or point of minimum equal to x, and we do not restrict the value of x in any manner. So we'll say this is the unconstrained maximization problem. Now we have already seen that if we know this function has a solution, has a maximum value at some point, then the derivative must attain a value of 0. We will give it a formal name. We will call it first order condition. If f of x attains a maximum at x star, then the first order condition is the derivative of f with respect to x equal to 0 at x star. When I say we will give it a formal name, this is the condition we will keep applying over and over. So I will write an abbreviation, first order condition, FOC. So FOC must hold. We use this first order condition to rule out all values of x other than those points where the function has zero derivative. X star will call these points to be critical points. X star is a critical point. So we will first figure out all the critical points where the function is derivative 0, because we know only these points are potential candidates for having a maximum value or a minimum value. And this condition itself is not sufficient in the sense that some of these points could turn out to be an inflection point. So for that, additional risk test will be required. Additional conditions need to be verified to claim that the point x star is a point of maximum or a point of minimum. And remember, we are not ruling out this situation where the point turns out to be a point of inflection. So that condition is typically called, we call this second order condition, which we will learn at a later point of time. So as of now, we will be able to write down an optimization problem and apply the first order condition. So, and then we will be able to obtain the function value. We can check whether the function has attained a point of maximum or minimum at that point. And so this is a good point to stop.